Okay. We're doing it, Chief. Um, yeah, I'm chilling and grilling. Okay, so I did a little bit more research. Basically, basically, I just scrolled down the Wikipedia page, and I discovered, there's a really interesting section called communication avoiding distributed algorithms. So I want to read more about these, right? Because like this is literally what I'm trying to do. I'm trying to partition a graph in a communication avoiding way. So I want to build a computation graph such that I want to build a computation graph such that I can take it and I can really easily split it up to be like communication avoiding. Or I guess what I want to do is I want to take an existent computation graph which satisfies some amount of properties, like all the nodes are distributed, distributive and or not distributive. They're communicative and associative on the inputs. So I want to take those and excuse me. And I want to take that graph and I want to split it up in a way so that it forms like a communication avoiding algorithm. Because that could be really sick. Yeah, okay. So I'll just read this whole Wikipedia page, this short Wikipedia page. But or actually, what's this? What are these references? Oh, yeah, okay. These sound like really cool references. Exascale computing study technology challenges in exascale computing systems. DARPA, yo! I'm gonna read a research paper from DARPA, bro. DARPA, DARPA. You know, DARPA is a word that's very easy to say in a dopey manner. DARPA. It can also be like kind of scary, like Interpol. Okay. Um. Oh yeah. So yeah. I guess I just want to read this, and then I want to read that. A modern architecture's hierarchy of memory, the cost of loading and storing input matrix elements tends to dominate the cost. Tends to dominate the cost of running a single machine. This is the amount of data transferred RAM into cache. While distributed memory multi-node machine is the amount of transfer between nodes. In either case, it is called communication bandwidth. The naive algorithm using three nested loops uses omega of n cubed communication bandwidth. Cannon's algorithm, also known as the 2E algorithm, is a communication avoiding algorithm that partitions each input matrix into a block matrix whose elements are submatrices of size blah by blah. Cannon's algorithm. Okay, yeah, that'd be interesting to look at. It's a communication avoiding algorithm that is each matrix input into a block matrix whose elements are submatrices. Yeah, where M is the size of fast memory. Ah, okay. So this is the cache basically. Um, the naive algorithm is used over the over the block matrices computing products of submatrices entirely in fast memory. Is used over the block matrices. Oh, okay, I see. This reduces communication bandwidth to O of n cubed uh, root m, which is asymptotically optimal. Oh, it's divided by root m. I see. Because the naive algorithm. Oh wait, no, it's omega n cubed. Oh, but omega n cubed is the omega is a lower bound. Wait, Is omega upper bound or lower bound? Oh no, I forgot. I think big O is lower bound. Which is asymptotically optimal for algorithms performing omega n cubed computation. In a distributed setting with P processors arranged in root P by arranged in a root P by root P 2D mesh. Okay, one submatrix of the results can be assigned to each processor, and the product can be computed with each processor transmitting that many words, n squared over root p words, which is asymptotically optimal, assuming that each node stores the minimum n squared divided by p elements. This can be improved by a 3D algorithm, which arranges the process in a 3D mesh cube, assigning every product of two input submatrices to a single processor. The result submatrices are then generated by performing a reduction over each row. Are then generated by performing a reduction over each row. What does that mean? The block matrix in each 2D algorithm, each process is responsible for one submatrix of C. In the 3D algorithm, every pair of submatrices from A to B that is multiplied is assigned to one processor. Every pair of submatrices from A to B is multiplied is assigned to one. Yes, I'm still a little fuzzy here, but someday I won't be fuzzy. I promise. Which is asymptotically optimal. However, this requires replicating each input matrix element p to the 1/3 times, and so it requires a factor of p to the 1/3 more memory than is needed to store the inputs. This algorithm can be combined with Strassen to further reduce the runtime. 2.5D algorithms provide continuous trade-off between memory usage and communication bandwidth. On modern distributed computing environments such as MapReduce, specialized multiplication algorithms have been developed. Oh, okay, interesting. There are a variety of algorithms for multiplication on meshes. For multiplication of two n by n on a standard two-dimensional mesh using 2D Ken's algorithm, one can complete the multiplication in 3, although this is reduced to half this number for repeated computations. Huh. Yeah, so I want to look at Kenan's algorithm, but honestly, I'm not entirely sure how useful it is, or how useful it would be in my particular case. Communication avoiding algorithms minimize movement of data within a memory hierarchy for improving its running time and energy consumption. These minimize the total of two costs in terms of time and energy: arithmetic and communication. The total in terms of time and energy: arithmetic and communication. See, I actually don't want to, like, as far as I'm aware, I just want to minimize communication. Memory hierarchy for improving its running time and energy consumption. Yeah. I mean, like, energy consumption would be cool, but more so, just like, yeah, that'd be cool. Communication in this context refers to moving data either between levels of memory or between multiple processors over a network. It is much more expensive than arithmetic. Yeah, yeah. Consider the following running time model. Measure of computation, time per flop equals gamma. Measure of communication, number of words, data moved, beta. Total running time equals gamma times number of flops. Beta times number of words. From the fact that beta is greater than gamma as measured in time and energy, communication cost dominates computation cost. Technological trends indicate that the relative cost of communication is increasing on a variety of platforms, from cloud computing to supercomputers and mobile devices. DRAM access time and flops will increase. Yeah. Reorganize algorithms to reduce communication across all memory hierarchies. Oh no, I'm out of water. Oh well. The following simple example demonstrates how these are achieved. Matrix multiplication example. Square matrices of order n by n. The following naive algorithm implements C equals C plus A times B. Arithmetic cost for sufficiently large n or O of n cubed. Rewrite this algorithm with communication cost labeled at each step. Since total running time is dominant, the blocked tiled matrix reduces dominant term. Read block AIK into fast memory, Write block communication cost. So, yes. I guess I just want to look at communication avoiding algorithm. Because like this is like literally what I'm trying to do, right? I'm trying to take an arbitrary computation graph and transform it into a transform it in a communication avoiding way. Or direct what? Of factorization and linear algebra. I mean, I don't really want to do factorization. Yeah. Is there a way to do just like general communication avoiding algorithm? For linear algebra and beyond. Why avoid communication? Algorithms have two costs measured in time or energy. Arithmetic, communication. moving data between levels of memory in a hierarchy, processes over a network. Running time on algorithm is sum of three terms: flops times time per flop, words moved bandwidth, messages latency. Time per flop. Gaps growing exponentially with time. Fosk. 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 Oh wait. Can I be heard better with that? Probably. Avoid communication to save time. Save story for saving energy. Redesign algorithms to avoid communication between all memory hierarchy levels. Obtain lower bounds if possible. Current algorithms often far from lower bounds. Large speed up and energy savings possible. Up to 12 times faster for 2.5D matmul on 64K for IBM BG/P. That's pretty fast. Hey, that's pretty fast. Nirvana deep learning startup acquired. What is this? All skinny QR. What is QR? QR is no, I'm thinking of spectral decomposition. What is tall skinny QR? Wait, is QR actually like spectral? Am I? Who am I? Yeah, I don't know, dude. But yeah, like I have a feeling that if you look at these algorithms, what you're gonna find is that their computation graphs, like they assign nodes to particular. You know what? Yeah, I want to look at the block tiled matrix multiplication. Ugh. I don't know. Like, I honestly I feel like I'm just like too stupid to like take all of this in. Like, because I'm gonna have to draw this giant graph, and then I'm gonna have to like somehow like parse it in my brain and like go over it and like understand it. And like I don't think I'm smart enough for that. Like I think I need a shortcut. Like, quite frankly, I just need a shortcut. Direct lower bounds on communication. Yeah. Blasts. What is CUDA blast? I'm sorry for getting off topic, but I never figured this out. Oh my god. CUDA blast. What is this? Wait, okay, so it's something basic linear algebra subroutines. Okay, well, that was you know what? I like it. I like when people make like the abbreviations or whatever that are like they're good. Bruh, I've discovered something. Okay, yeah. They just stole this from Wikipedia. Or did they? 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 It looks suspiciously similar. Oh, okay, actually, it looks very different. C equals C plus... Oh, okay, I see. You reuse C or whatever. Read ith row of A into fast memory. Read Cij into fast memory. A, B, C to be N over B, N over T, matrix C, N over B. You have these sub-blocks where B is called block size. Assume 3 by 3 blocks, or 3 B by B blocks fit in fast memory. For I equals 1 to N over B. Read block Cij into fast memory. Okay. For K equals 1 to N over B. AIK. Yeah, just okay, do matrix and then you write. I see. Interesting. B squared times N over B squared equals N squared rights. Oh, I see. Oh, wait. Yeah, okay. Wait, what? N over B squared. Why is it B squared? Oh, because the block itself is B squared by B squared. Okay. B squared times N over, okay. That makes sense. Uh, oh. B squared over N over B cubed. Oh. So N cubed over B. Oh my gosh. My brain is in recovery mode from taking in all of these high level ideas. Oh my god. Wow, that's really, really simple. Oh, yeah. Okay. Faster! Yo, but what if we don't know M? Bruh. What is M? Cache oblivious algorithm. Bruh. N by n mat mole on p to the 1/2. So it's just a p grid. P grid. uh, you know what's really fantastic um is that in like English syntax studies they have prepositional phrases, right? But like they don't want to write that up, so they abbreviate it and it becomes PP. Okay, but serious mode. Let's get real here. B is the block size, the number of columns, and AIK. I assume AIK is like the matrix. Oh, no, it's not. Wait, is it? The number of columns in AIK, number of rows in BKJ. Okay, I see. I vaguely understand. For all I equals 1 to P 1 over 2. The square root of P. Okay. Owner of AIK broadcasts it to whole processor row. Using binary tree? What does it all mean? Broadcasts it to whole processor row using binary tree. For all j equals 1 to p to the 1 over to the square root of p, the whole processor column using a binary tree. What does that mean? So I broadcast. I assume it does something. Receive AIK into A call. Receive BKJ into B row. See my proc. See my proc. See more butts. Okay. C my proc is equal to C my proc. A call times B row. This is definitely not as clear as the other one. Yeah, I'm really confused. It's a whole processor row. So we outline our processes in a grid such that like this is one thread, this is one thread, this is one thread, this is okay, so this thread is computing this thread is computing this thread is computing this thread is computing this. Assume n by n matrices on p processors. Minimum memory per processor equals m. Recall lower bounds. Words moved and the messages. Does Scala pack attain these bounds? For words moved mostly except non-sim eigenproblem. Non-symbolic eigenproblem? Non-symmetric? I assume non-symmetric, yeah. For messages asymptotically worse except Cholsky. New algorithms attain all bounds up to polylog p factors. Are we already optimal? Why assume m is O of n squared over p? Lower bound still true if more memory. Can we attain it? Special case. 3D matmul. Use